Hi, I'm Brian from Simply Brian Enterprises and welcome to my channel. In today's video, we're going to be looking at the homework solution for TopTechBoy's Raspberry Pi Pico class, lesson number 6. In this lesson, we're taking the potentiometer that we worked with in lesson 5, and instead of just printing out numerical values in the console, we're actually going to use the LEDs to represent some visual output as well. So, as I normally do, I want to take a look at the hardware, run the program, and then we'll dig into the code. So first off, we'll look at the hardware. So the potentiometer hasn't changed since last week. I've just left it connected to the same GPIO pin, the ADC input. However, you see I've added 3 LEDs. I've added a green, a yellow, and a red. And I've jumpered them to the GPIO pins. I think I used 11, 12, and 13 using these longer jumpers, again with kind of the curvature. Um, I like this a little better. I think it's nice and clean. I was able to find a red jumper the right length, a green jumper the right length. Unfortunately, I couldn't find a yellow jumper that was the right length. I'd use white. But I think it still looks nice. I think it worked out pretty well. And of course, I used my handy dandy little card that came with the Kepler kit. And you might notice, I don't know if you can see this, it's kind of hard to read. I've actually started writing pin numbers on here because there are numbers on my breadboard. It goes up from 30 on the far end to 11 on this end of it. And so I've started to put them on the card so that I don't have to do quite as much counting and guessing when I'm using new GPIO pins. So I just thought I'd show that. That's kind of handy, especially if your Pico doesn't move much. If you leave it on the breadboard like I do, you can actually put the extra numbers on there to make it a little easier to find the pins since they're not really marked any other way. Another thing I wanted to talk about is resistors. And so we have this very nice pack of 220s, very large, nice pack of 220 resistors in the Kepler kit. However, unfortunately, the only place they're labeled is on this sticky tape. So when I take a resistor off, um, I don't have any way of really referencing other than the bands. And quite honestly, it's kind of hard to read the bands sometimes. I'd rather not read the bands if I don't have to. So what I've come up with for this is when I use resistors, like I've got these 220s here that I've clipped shorter. I've got the 12 millimeter legs on them, so they sit nicely on the breadboard. Once I take them off the tape and clip them, I want to be able to put them someplace safe. And what I found are these little guys, and these are referred to as jewelry bags. You can find them in the craft section at any store near you that has a craft section, I guess. I found this, bear with me here. I found this at my local craft store, 100 pack for about $2 of these. And what I did is I took the baggies and I took my label maker, and just give me a second here, I'll show you. So inside the bag, if you can see that, I actually printed off a label, 220 ohms, stuck it inside the bag so it's nice and solid. And now I have a nice baggie that I can put these used trimmed resistors in. And now when it goes back in the Kepler kit, I can easily figure out which resistor is which. And as we go forward with the Kepler kit and do more projects, we're going to be using more and more resistors. So I think it's going to be really handy to have the ability to have little baggies of our resistors to make it a little easier to find them. So I just wanted to go through that really quick because I thought that was kind of a neat help. So let's get on with our program for the week. So what Paul had asked us to do was um, design a program that as we start at 0, we have no output, but as we start to move the potentiometer, we have a green light if we're less than 80% duty cycle. And then if we cross that 80% threshold, we're going to get a yellow light, a warning that we're drawing too much current in this circuit. And then if we reach, I think it was 94% that Paul told us, we get a red LED of danger. We're overloading the circuit now. And so what I've done also is, if you notice, there's the LED, the onboard LED on the Pico. When I go all the way to the left, it not only turns off the green LED here, it shuts off here. So basically I've got what's essentially a power light. I turn it on regardless of my output value, the power light is on. So that's the program running. Let's take a look at the code. So the way I've got this set up is I'm importing Pico pins separately. I like using Pico pins, so I imported that as its own. And then I've brought in machine and time as well. I'm setting up my LED pins, my green, my yellow, my red, my onboard, and then reading from the potentiometer. I chose not to set a variable here because it would just be an extra line, and I'm basically defining it here. So if I did change my input pin, I could change it here. I don't think it's a big deal. Using the minimum and maximum from our last lesson, 365,530 is the minimum and maximum. And then calculating the differential is the difference between the two. And then I'm setting our thresholds. So we want to trigger the yellow if it's greater than 80%. We want to trigger the red if it's greater than 94%. And you'll see why these are off by 1, 81 and 95, when we get into the if statements. So just like last week, I read in the value and then I set those edges again. So I go 300 on the low end, 65,530 on the top end, and I don't want it exceeding that. And the equation that I used this week, I brought in the one from last week because it's so similar. Really, the only difference, let me grab this really quick. Yeah, I'm going to flip back to the table view quick. So last week, we used a negative slope from 100 to 0. This week, we're using a positive slope from 0 to 100. So in order to do that, we can take the same exact equation. All we have to do is we have to invert our slope, which is negative 100 last week, to positive 100 this week, and then just change the y-axis. Instead of intersecting at 100, and I think we figured it was about 100.4 was our y-axis intercept last week, we're going to come down here to where x is 300 and y is 0, and we're going to end up with an x or a y-intercept of about negative 0.4. So all we have to do is we have to change the negative 100 to positive 100, and then we'll take that plus 100 offset off of there, and we'll end up with a y equals mx plus b equation that mimics perfectly. And you can see here I just changed the negative 100 to positive 100. And then just to demonstrate, I changed the plus 100 to plus 0 as our y offset. And again, that gives us that y-intercept of roughly negative 0.4. So now we come down here. Here's the new stuff that we're doing with the ifs. So we're going to make decision based on the threshold. If it's 0%, oh, one important thing. So what I'm doing here is I'm calculating the value between 0 and 100. I'm forcing it to an integer because I don't want um, decimals here. I just want to have the integers because when I'm doing my if statements, it's going to be a little easier if they're full integers. So 0% is off. Greater than 0 but less than yellow is green. Greater than yellow but less than red is yellow. And greater than red is red. So the first thing I'm going to do is I'm just going to look and say if my value is greater than 0, turn on the onboard LED. That means basically unless it's all the way to the left at 0, the onboard LED is going to be on. It's going to have that power light on. And if not, if the value is 0, set all of the LED values to 0. We're shutting them all off because this is our off position. So now we get into the real if statements. Now we're going to decide, are we between greater than 0, meaning we're on at least a little bit, and are we below yellow? Again, remember that this threshold yellow is 80 plus 1. So this means that we have a value of basically between 1 and 80. I've excluded, notice I've done greater than and less than, but not equal to. So that's basically saying if the value is between 1 and 80, it's green. And of course, you can see here I'm only turning on the green LED and I'm leaving the other two off. I saw a couple other solutions where people were using things like lists and functions. There's definitely more elegant ways of doing this, but I'm still erring to the side of doing this homework as a beginner class, and so I don't want to get too fancy just yet. There's time for that in the future as we get into more advanced ideas, setting up things like functions and lists and dictionaries and so forth. We'll be able to do some pretty cool things and make these programs more elegant. But today we're just really walking through the simple steps of this is how we make the program work. So now I have exceeded my 81, so I'm 81 or greater. I'm threshold yellow, and I'm less than red. So I'm between now a value of 81 and 94. I am going to be yellow. And then if I'm greater than or equal to 95, then I'm going to be red. And I'm just printing this out to the console so I can see the value of my resistor. And if you look below, you can see as I turn it up, this changes. Here I'm going up. See, I just hit in the 80s. Now it's yellow. And then I can hit all the way to 90, almost all the way up to 100, and it's red. And I can back it back down, and I can actually turn it all the way off. And then we're registering 0 again. And the only reason the sleep is in here is just to keep the console from flooding, slowing it down enough so that I can read it. And that's the only reason it's there. But there's another aspect to this program that I thought about. And, Paul used the example of something like a motor, right? So we want to run our motor. Generally, electrical devices are best run at about 80% utilization. If you push it higher than that, that's when they start to wear out faster and break down. And certainly electric motors are that way. They run about 80%, and if you push them too hard, they tend to wear out. But if we use that motor example, have you ever noticed the switch on a window fan or your ceiling fan or perhaps maybe like the hood on your stove? It starts off at 0, but then as soon as you turn it on, it goes to high, and then as you turn it down, it goes lower. You ever wondered why that is? Well, there is a reason for it, and it has to do with how motors work. If we started off motors with a gradual voltage, a very low voltage, and just gradually inched it up, we could actually end up in a state where the motor doesn't spin. It just sits and hums because it needs a little bit of a jolt to make the rotor actually move. And so that's why you'll see in a lot of motors, you actually go to high first so that it forces that jolt to make the motor spin. So I was thinking about that, and I thought, well, maybe our code should reflect that. So let's go back to a different program I wrote. Very similar program. In fact, really the only difference is I've gone back to my previous equation because now I want to go again to this. We're going to start off at high and we're going to move to low. So I want this negative slope in this percentage value. So we're basically using the same equation as last week. And now I'm going to run this program and we can see, whoops, I didn't have it all the way off. So now I have it off, and then I'm going to turn it on just a little bit, and you can see I immediately go to high first, and then as I turn it, I go into low. So this is, again, if this was like your window fan or a ceiling fan, you pull the chain once, it goes to its highest speed, and then you pull it again and pull it again to slow it down. This is kind of the same idea. We're actually turning it up to turn the motor down. Just like a control on an actual fan motor. So I thought that was kind of an interesting idea. If you like this video, be sure to hit like and subscribe below. Thank you to all my new subscribers. Appreciate the comments and the views. For Simply Brian Enterprises, this is Brian, and I will see you next time. Thanks for watching.